This is stop number 3 as part of our 2022 Great American Supercomputing Road Trip. We are here at NCAR, and man, is this place beautiful. If you haven't been here, put it on your bucket list. This is one national lab you've got to see. I'm here with Brian and Thomas, and please introduce yourselves.
Go ahead, Thomas.
Hello, Dan. I'm Thomas Hauser. I'm the acting director of the Computational Information Systems Lab at NCAR.
Excellent. Great to meet you.
Hi, Dan. I'm Brian Vanderwende. I'm an HPC consultant in our HPC division in the computational lab.
It's a good place for an HPC consultant to be, in the HPC division.
Yeah, I think I did a good job.
So tell me a little bit about the lab's mission here.
Yeah. So, obviously we're the National Center for Atmospheric Research, so we like to focus, our mission is to focus on climate issues, weather issues, any sort of, atmospheric phenomena, oceanic phenomena.
Long-term, mid-term, short-term.
Yeah,
right?
For sure. We scale from, studying anything from, say, a tornadic system that moved through the Great Plains and caused a lot of destruction, figure out in a sort of a hindcast what happened there, so we can have better forecasts in the future, all the way up to, the big climate simulations that are part of like the IPCC report and all of that work going on at the United Nations and things like that. We play a prime role for the U.S. science there.
I'm going to bet that takes a bit of hardware to be able to do that kind of computation. You tell me a little bit about what sort of systems you have here?
Sure. So we have, our current production system is Cheyenne. It's about a 5 petaflop system. It's entirely comprised of CPUs, but we also have and those are going to be dual socket Intel Broadwell nodes. So.
Yeah, I saw that in 2018 when I did this trip. I stopped by the Big Boot to take a look at it. It's very impressive.
Yeah, we've got that system in most of our systems at this point up in Cheyenne, Wyoming. So that's obviously why. The system is called Cheyenne.
Yeah.
We also have Casper up there as well. That's our data analysis system, and that's a bit more heterogeneous. So we have GPU accelerators in there. We do data analysis with that machine, and that's also has a bit of our footprint for a bit, more of our exploratory efforts in terms of machine learning and just ways to accelerate our codes.
Yeah. So Thomas, what sort of software are you running?
So we're running all kinds of climate models. So the Community Earth System model is one of our biggest users. Because it's a community model, so everybody from university researchers to NCAR staff, and also for teaching is using that model. But we also run machine learning software right now for we have lots of applications. NCAR has been really doing machine learning for a long time. And then also, don't forget about our solar physics. We have MURAM, which is a solar physics code that studies kind of the solar corona and solar winds, because that influences our Earth's climate.
That is a good point, not something that most people would know right offhand.
Yes, I think, and we are working a lot with them. It has become a community model, and it's an international effort. Working with the Max Planck Institute in Germany, with the University of Chicago, with researchers at universities and at NCAR.
Okay. And you mentioned machine learning. What's the major use of machine learning? What is it buying you?
The major use, it's still very diverse. So we do a lot of different applications. I think one of the biggest promises that I can see is speed to terms of classical approaches. So we are looking at chemistry networks. The reactions in atmospheric chemistry, and I think we see 100 to 1,000 times faster results when we do recursive neural networks.
100 to 1,000, that's not bad.
Yes, that's really good.
That's a win, we call it.
Yeah, and that's much better than traditional acceleration efforts we do. So we do a lot of work in preparing for the next generation for heterogeneous computing, for the Retro, which will be our system that is coming online next year that has 20% GPU. So we prepare for that. But then the speed ups is like in the order of maybe 4 to 5 versus 100 in machine learning.
Okay, but do you need those accelerators in order to build those neural nets and have them perform?
Yes, we do. I mean, this is the key application or the easy application on utilizing GPUs, neural networks. Porting our model is a much harder effort, and we are discussing this, and it depends on the complexity. We have already a few wins, codes that run fully on GPUs, but there's still a lot of work to be done to accelerate our models.
I would imagine that that's massive. Is the lab using public clouds at all?
So we are, yeah. There's definitely a pretty diverse mix of most of our stuff is on-prem, but we do have modeling groups who are using the cloud to do training events. They basically package up a small version of a small test case in the model in a container, and then deploy it in a cloud platform, and then they can get access to people, anywhere, basically in the world for these training events. They don't have to get accounts on our resources and do all this stuff. They can do something in a very cloud-native sense. The other thing that we're using the cloud for is sort of a backup. So we have a prime example for this is our Antarctic Mesoscale Prediction System, or AMPS, and this is used by the science team to basically make forecasts for the next week ahead for the researchers in Antarctica. And obviously, you've got some pretty nasty storms that can move through there, especially in the winter. If you've got a supply flight that you're relying on to bring in food and maybe new researchers or bring people home, it's crucial that you have a good forecast of any nasty storms.
They're looking to make that flight.
Yeah, for sure.
Want to know.
Yeah,
it's going to happen pretty local.
If you're going to stay in New Zealand or if you're going to actually get down to the base. So that sort of simulation, we don't do a lot of say critical forecasting here. We do more retrospective and climate. But that's one example of where we've got a product that needs to get out.
That's very critical.
And it runs on Cheyenne typically, but we're now using public cloud as a backup there. So if we have a downtime or an outage or something on Cheyenne, we can basically burst their simulation out to the public cloud and make sure that forecast still gets out.
Interesting. Kind of, you were talking about having a new system coming up. Are you looking at all towards some of the new stuff that we're hearing about with like CXL and composable infrastructure and different ways to be able to put a system together?
Sure, I think
that's hardware, software.
Yes, that's a difficult question. So I would say the retro was started 2 or 3 years ago, the purchase. So for that system, we don't. But I think we are closely following the developments and looking at maybe experimenting with that technology, partnering with some of our university communities. Like I think Texas A&M has a composable system. So we are looking at that technology and how that can inform our future kind of procurements and systems, and how do we put workflows together.
Yeah, it's going to be an interesting new world if the promise of it comes through. I mean, what do you think, Brian?
Yeah, I think it's like Thomas said. I think it's something that we need to keep an eye on. I think there is a lot of promise there, like you say. I mean, the procurement process for derecho was pretty traditional. I mean, obviously, there's the challenges that everybody in the industry is dealing with. But in terms of how we architected the system, the main new thing that we were excited about was the accelerators. Yeah. So at this point, we're certainly taking a look at composable architecture and stuff like that. But
it won't quite be there yet, though. You need to have PCIe 6.
Yeah.
You need to have a few more pieces slide into place. How big is the new system going to be?
So it's about 20 petaflops, with, as Thomas said, about 20% of that provided by GPU and the rest provided by AMD Melange CPUs. And
that's going to be, what, 4 times bigger than Cheyenne?
It's over 3.
Over 3,
yeah.
Okay. Great.
Yeah, I'm super excited. Just waiting for the hardware to be delivered in December, and then we are ready. I mean, the facility is fully prepared to receive. We did all the fit up that we could do without the system, so we are ready to get the system up and running.
Now, here's going to be what you think is going to be a stupid question. When are you going to exascale? Is that on your long range of things?
Speak to that, Tom.
I think NCAR, I would say probably long-term, no. But I think we are using our system as a stepping stone.
Yeah.
So the system, we have an exascale initiative on how do we port our codes, as I mentioned before, to GPU-accelerated architectures. And I see our scientists kind of explore, scale, debug on our retro system or the next system or maybe the system after that, and then go for the real big workloads to the DOE systems that are exascale. So we already have codes and benchmarking that were done on Summit to do the GPU. Okay. And so I expect similar that we're going to use some of our code that work on Accelerator on Frontier when Frontier becomes more publicly available.
That would be good. So are you both going to, or either one of you going to SC22?
Yes. I'll be going virtually. I think you're going in person.
I'm going to go in person. I really look forward to meet people and connect and learn. And I mean, I think that's for me the biggest. I mean, the technology there is also, it's amazing, but reconnecting. I have seen a few of my colleagues not for quite a while since the pandemic. So I'm really looking, and I hope there's a good turnout in person as well.
I hope so too. Do you need a ride? Because I'm driving there.
You're driving there from here?
That's whole part of the trip. I'm driving there from Beaverton, Oregon.
Okay.
So that's my big trip.
I'm going to fly. That's my
You sure?
Yes.
Okay, just thought I'd offer. Is there anything particular either one of you are interested in seeing or hearing at SC22?
Yeah, I think for me, I'm pretty interested in seeing, we've got a lot of obviously societal challenges right now, and climate change is such a great example of that. It's part of the reason why it's exciting to work here at NCAR. But I think right now with a lot of the convergence of sort of philosophy and technology and approach between like private sector data centers and the cloud, and what traditional supercomputing is doing, there's a lot of potential, to really attack these problems in new ways. So that's one of the things I'm excited about. And obviously, as Thomas said, there's just reconnecting after this strange past few years, is always good. And just seeing the increasing diversity in the field as well, both in terms of approaches, but also just, the types of perspectives you see in supercomputing. I think that's something that is, crucial and still have a long way to go. But, every time you go to SC, you see more and more of it. So
You do. Okay. Getting close to winding this up, here's a key question. Assume that you're addressing the entire HPC community of vendors right now. What is it that you need from them in 3 years? What do you need from them? What do you want from them? And the reason I ask 3 years is because they can change the direction of what they're doing in that amount of time. In the next 12 months, not so much. 3 years gives them a chance to make some changes. So hardware, software, systems, what do you want? What are they not doing even?
From a software perspective, I want more portable approaches to accelerator programming, making sure our investment there's more of a standard, so our investment in porting these codes is preserved. I think that's, for me, one of the key.
So now, are you saying that if you had a CUDA version, you would want that to run on the AMD accelerators or the Intel accelerators without major change?
Yes, that's one example. Also OpenACC or I think better quality Fortran compilers too. Making sure Fortran is early on supporting GPU acceleration. There's also, some, for me, very interesting developments in the language, kind of offloading in Fortran or in C++ directly to the GPU. And I would love if that becomes standard and performs better, so we can focus on standard language features compared to additions like directives or CUDA approaches.
I need to introduce you to my new buddy. Her name is Goshen up at Pacific Northwest National Lab, who's working on kind of a universal compiler.
Yes, I would be very interested in. Part of my division is really to explore what's the future, and that then can we translate that into our community codes. And again, compiler-based approaches, universal compilers, that's something I'm very, very interested in.
That would be very nice. It's going to be hard.
I'm not saying this is easy, but they have 3 years, right? So you mentioned that.
That's true.
What do I want?
That's okay. That's good. So how about you, Brian?
Yeah, I think from a hardware perspective, something that's tractable and something that we're seeing a lot more interest in from our researchers is sort of the power envelope of simulations.
So too low a power?
No, it's yeah. No, everything's just too efficient. No, and I think this is something that accelerators have helped with, but really what people want is information on their power usage. We work at a climate lab, a meteorological lab as well. Our researchers are telling us, I want to know the footprint of my simulation. And obviously, I think the science is valuable, but I want to see what that science value is relative to the power that I'm using. Our supercomputer is up in Cheyenne, and we're making more and more efforts all the time to get clean energy to power the system. But that's a process. And I think in the interim, what the vendors could really provide us with is more tools and just more integration in terms of power monitoring and also controls on that. So, giving our researchers the switch to say okay, well, I'll run this maybe at 20% lower, power threshold.
CPU frequency.
Yeah, CPU frequency, or even clocking the GPU or something like that.
Yeah. I can wait for the answer, so I'll spend less power on it.
Yeah, and we can put that into a charging algorithm or something like that, and basically let people make informed decisions about that.
It's funny. I've been involved with the student cluster competitions, and this time even more so. And there is not a lot of software out there that will really tell you, for instance, on AMD processors, or give you the ability to ramp them down in graceful steps. And what's funny is that the computer enthusiasts, the gamers, they have all this stuff, and they can monitor it in real time. But we don't have it in HPC.
Yeah, if you want to put your big liquid nitrogen block on your CPU and monitor what's going on, you can do that. But if we want to look at the the output of a NVIDIA GPU, there's NVIDIA's DCGM, the data center GPU manager. So it's developing, but it is behind. I agree.
Yeah, and it's. I was just at a conference, an HPC Advisory Council conference, and they did about half a day on this. And that was one of the exact things that came up, was that their scientists, their people wanted to know what the power cost was going to be in particular runs.
Yeah, and I agree. I always talk about now, especially in the future, time to solution and energy to solution, right? And these two, and I think this ties into what Brian just said. So I think that's important to have the support, the tools, so we can make informed decisions.
And that's kind of the argument, though, that being faster to solution gives you more science per watt. Or does it? Depends on the job. It depends on what you're trying to do, right?
Yeah, it depends on our workloads, right? A lot of our workloads are memory bound, so maybe the GPU, the compute is not quite as important. But again, we need to measure that and be able to really get the information there.
Yeah, I think you want to attack the problem from both sides, right? Obviously, you want a faster time to solution. That's going to, produce a more efficient process, but having that information on the back end in terms of what you're using for power is also crucial.
Yeah, very much. Let me ask you a final wrap-up question. What excites you about the future of supercomputing?
For me, it's the diversity of architecture suddenly. We had, that's exciting and scary too at the same time. So, but I think that's for me exciting. I think there are opportunities with kind of new hardware developments, kind of the heterogeneous development, accelerators for machine learning. How can they be used in our model? So that's really, really exciting. But it's also scary looking at our model developers, and it goes back to our universal compiler, right? How do we utilize this diversity of hardware efficiently from our codes, where we don't have to change as much, right? We don't want to, every time a new hardware architecture comes in, change our codes. It's just impossible.
Because you're making a bet, in essence.
Yeah.
And there's a risk there. How about you, Brian?
Yeah, I think this is, it's part of the pipeline. It's maybe a little bit HPC adjacent, but I think some of the interesting things to me, what excites me, are some of the pipelines that are getting developed from like our model codes direct to a data analysis or machine learning workflow or something like that. Like we've been looking at this Smart Sim library recently, which basically handles in memory the transferring data from a running simulation to like a machine learning model, and that could inform how you parameterize the physics. It could actually replace the parameterization of the physics in some cases.
It could certainly take a lot of brute force out of it.
Yeah, for sure. And again, you're leveraging some of the developments that are coming in from like the business sector and other things. And we don't want to get left behind by those technologies. We want to leverage them. So I think that sort of like full pipeline analysis and trying to make that more efficient, so you don't have to go to an entirely different framework while you're running your simulation. To me, that's really exciting.
That's very cool.
And don't forget about data.
Nope.
I mean, we have large data sets. I mean, NCAR is a data repository. And so one of the things we want to bring compute to the data, so people can efficiently...
data to the compute.
Exactly. So can do efficiently their analysis. So.
How big is your data store? I mean, roughly, rough terms.
We're like over around 100 petabytes on our campaign storage. We have a 60 petabyte scratch coming in as well. So all of that data obviously gets generated and then needs to get moved to something that's a little cooler. So right now we've got a bunch of tiers. We have our campaign storage, which is disk. That's going to grow to over 100 petabytes, I think, in the next few years. And then we have a tape library as well. We still have that kind of running in the background, but it's not our main archive anymore. And then I think to Thomas's point, we do have groups now that are hosting data sets directly in the cloud. They're partnering up with these cloud vendors. And that's exciting both for our researchers because it provides more access, but it's also just exciting because we have our big university community and our other partners, and they can access the data that our scientists are producing very easily.
Last question, what kind of weather am I going to see between here and Dallas? I went through the 75-mile-an-hour winds coming to Laramie, getting through there.
I think you're asking the wrong people here. We are on the computational side. You need to you need to go to our scientists.
Get the Antarctica program working on this.
Oh yeah, I don't say we can't do it. I think it's just us. We are really in charge of accelerating and providing the infrastructure. I can't give you a weather forecast.
So tell me the Weather Channel then, basically.
Go to MCube, our weather lab. They can give you. I mean, that's what I'm saying. I mean, we are here to provide the infrastructure, and we're working closely with them, but we are not the weather people. Go to
MCube. Take me over there.
Yeah, the windstorm will actually blow you in the right direction to that building. So,
well, thank you both so much. Really appreciate the time. It's been a great interview, and we will see you at SB22. We will see you online. Thank you very much.
Thank you.
Okay.